Hi everyone, I'm Parsh Jain, and I'm excited to discuss today our work on contrastive code representation learning. We develop a new self-supervised learning method to learn high-quality representations of code using unsupervised data from big code repositories such as GitHub. Our work demonstrates a state-of-the-art performance in a variety of different downstream tasks when we fine-tune our representation. This work is joint work with Jay Jain, Tianjun Zheng, and Peter Abil, Joey Gonzalez, and Jan Stoika. So machine-aided programming tools are becoming increasingly ubiquitous today. Developers rely on tools such as automated security analysis in tools such as GitHub, code auto-completion in IDEs, program synthesis, often found in spreadsheets today, and code search. But the state of the art in these tools are increasingly learning based. So in fact, across the board, from deep code search, code completion, program synthesis, to automated bug fixing and code summarization, machine learning is instrumental in achieving high accuracies. However, there is a unique challenge in the program domain where annotations are relatively scarce. This may be due to the fact that programs are relatively difficult to annotate and require expert knowledge from developers as compared to, say, annotating classes of images. However, in the largest dataset, one of the largest datasets for machine learning for code, the CodeSearchNet Challenge, out of 2 million JavaScript programs in the dataset, less than 160,000 of these programs have annotations. So the current practice today is to perform self-supervised pre-training using architectures such as the BERT model. The key idea is to reduce code to just simply plain text, a sequence of just plain text tokens, and then pre-train a contextual embedding of the sentence, just like you would do in natural language processing. In this case, though, on lines of code. During BERT pre-training, the pretext task is to perform masked language modeling, where the model attempts to predict corruptions or masks tokens in the source sequence, and a next sentence prediction task. However, we find when probing the representation learned from BERT that it doesn't preserve semantics. So in fact, we have a t-SNE projection of the RoBERTa embeddings. So each color here represents a set of equivalent programs. So ideally, we would like for the representation to respect semantics, and specifically here, just the operational semantics of the program, meaning that two functionally equivalent programs should have very similar representations. But in fact, if we look at this cluster in the representation, we can see that a variety of different functional equivalent programs between different clusters overlap. And so here, it doesn't cleanly separate between different source programs, so it isn't really strictly preserving semantics in the learned representation. So this wouldn't inherently be a problem by itself, but prior work actually discusses the sensitivity of code representation models to semantics preserving transformations. These transformations don't change the functionality of the code, but they end up oftentimes dramatically changing the resulting label of the model. So what makes for a good code representation? In our work, we consider that programs with the same functionality should have similar representations in latent space. So given a particular source program, such as a for loop in this case, the representation of an equivalent program, perhaps with a substitution of the for loop for a while loop, should be very similar. But different programs, for example, some kind of string manipulation program, or maybe some kind of recursion, these programs should have different distinct representations as they're functionally distinct or functionally different. So in order to encode this invariant into our representation, we utilize the Contrastive Code Representation Learning method. This methodology considers a data generation phase where we utilize a compiler to take a series of source unlabeled programs and then generate a series of augmented variants for each of these programs. So given a particular source function, such as a for loop, the compiler will automatically generate different variants using different constructs, such as a while loop, perhaps utilizing loop unrolling or different transformations. So these are different functional equivalent programs, but they are textually distinct. And we can utilize each of these sets to perform contrastive pre-training. Short, where we'll just sample two particular samples from the same functional equivalent set, embed them both, and maximize the similarity of these two representations. We'll also try to push apart the representations between each of these embeddings and a historical batch of known negative programs that are functionally different. And so this simple mechanism, which is strictly unsupervised and requires no labels, learns high-quality representation of programs that maintains this property where we want functional equivalent programs to cluster together in representation space, to have similar representations. Finally, we can fine-tune this representation on a downstream task. And oftentimes we can apply this to a task which is relatively data scarce. So in contrastive learning, this is a framework that attempts to pull similar pairs together while pushing dissimilar pairs apart. And so here, the samples of the car are pulled together while samples of elephant are pushed apart from the car. And this is closely related to instance discrimination. Now, the influency loss used in contrastive learning is actually quite a powerful loss function, and it learns very high quality representations. With self-supervised pre-training, in this case with contrastive learning, and just a simple linear probe on top of the network, the SimCLR v2 network is able to accomplish a 73.9% top 1 image accuracy with just 13 labeled images per class. And so contrastive learning is demonstrating remarkable progress in image processing. In the contrastive setup, say with SimCLR or the MoCo architecture, these models utilize data augmentation to derive similar equivalent samples, in this case, views of the same source image. So in the left-hand figure, from the same source image, in this case a dog, data augmentation derives two different views using cropping. Similarly, we can derive two different views of a particular chair. And the influency loss learns to repel images of dogs, in this case, from images of the chair because they come from a different source instance. Now, in the code task, where do we get data augmentations? In our work, we utilize a compiler. A compiler can automatically apply different semantics preserving transformations to the program to derive a variety of different augmented program variants. So in this case, we perform a variety of different augmentations such as dead code elimination, identifier mangling, line subsampling, type up conversion, and constant folding. And this derives a wide set of transformed program variants. Now, programs with the same functionality should have similar representations. And this is exactly what we want on a representation. And so we're able to accomplish this by using these data augmentations from a compiler. Consider a merge sort. We can utilize these transformations to derive these two different views shown below. I'm not going to go into too many details here, but these are substantially different from a textual basis from the source program. However, they're effectively semantically equivalent as they have the same functionality. At runtime, they perform the same exact sequence of operations. So contrastive code representation learning, as our methodology, utilizes these augmentations to then perform contrastive learning. Now, when we consider fine-tuning this representation of a variety of downstream tasks, how well does our pre-training perform? First, we consider type inference on the TypeScript programming language, and we utilize the deep typer dataset. We consider a variety of baselines, including static analysis baselines, as well as supervised learning baselines, including the transformer model, the deep typer model, and finally, RoBERTa pre-training. Across the board, ContraCode outperforms prior baselines when combined with a particular backbone architecture. And it's able to significantly outperform the deep typer architecture in both top 1 accuracy and top 5 accuracy. On a code summarization benchmark, we consider, given a particular source program, we wish to label what does this program do using a textual representation. So for this particular JavaScript snippet, the goal is to summarize it as submit form. On this benchmark, we find that our model significantly outperforms prior supervised and unsupervised baselines when evaluated on F1 accuracy. Finally, we consider a zero-shot code clone detection task. Here, we wish to detect whether two student programs are functionally equivalent. And so we evaluate this task using a linear probe network and a cosine similarity loss. And what we're considering here is a zero-shot setup in order to compare it to the linear probe setup in self-supervised image processing. Again, what we find here is that ContraCode significantly outperforms both supervised baselines as well as mass language modeling. Finally, we probe the contrastive learning representation space in this case. And unlike the RoBERTa embedding, where we saw a significant overlap between functionally equivalent programs in representation space, all functional equivalent program sets are neatly clustered, and each color class is distinctly separated. And this also applies if we consider a hybrid loss. So I'm very excited to talk about contrastive code representation learning, a new self-supervised algorithm to learn high-quality representations of source code. If you're interested in our work, please come by our poster later today. Thank you very much.